mathematics, computer algebra, geometry theorem proving, and regular theorem proving for long before any of us, I think. And just he comes out with surprising and amazing results every year. Another one of these.
Can I start? Okay. So I'm going to discuss parametric Groebner basis primarily at the request of Grant and Leo, but I'm hoping that others will get interested also in this. Many of you may not have heard about Groebner basis, even though James alluded to that quite a bit in his talk. So please stop, interrupt me anytime, and it will be good to have an interaction. It doesn't matter if I'm not able to cover everything. So this is joint work that's been going on for almost now 8 years with Professor Sun Yao and Din Kong Wang of the Chinese Academy of Sciences and my former student Yimin Yang. So just to give you the background, since many of you may not know about Groebner basis, it was an idea that was actually algorithm proposed in Bruno Buchberger's PhD thesis in 1965. Basically, around the same time Penultimate completion came around. So this is kind of sort of the first instance of completion algorithm that was there, and for a long time. So for a long, it basically called them Groebner basis after his thesis advisor, Groebner. But then he has told me all kinds of stories about Groebner. Probably Groebner had never read his thesis. But Buchberger became very famous. So then in 1992, Volker Weispfenning, to whom I have the honor of introducing Groebner basis, and he proposed this idea of comprehensive Groebner system and Groebner basis for parametric polynomial systems. And then around the same time, I did not know about his work, and around the same time I proposed also the notion parametric Groebner basis. So I'm going to be interchangeably using the word parametric or comprehensive. I think parametric gives a little bit more insight, but comprehensive has become a lot more popular, so we'll see how it goes. So what are the applications? So Weispfenning was mostly interested in algebra. So he basically was interested in solving systems of parametric polynomials under various specializations, and you will see examples of that in a minute. Also, grouping together structurally similar polynomial system under various specializations, essentially meaning whether for various specializations they have no solution, finitely many solutions, infinitely many solutions, and what is the dimension of those solutions, etc. I got interested in Groebner basis, parametric Groebner basis, actually Groebner basis as well as parametric Groebner basis from an automatic geometry theorem proving point of view. But to justify my existence at General Electric Research and Development Center, that's where I was after my PhD, I was doing this stuff in the context of scene analysis and image understanding, trying to compute invariants of objects, and those invariants could be used for recognizing objects in a scene. More recently, in the last 5 years, I've also found applications in program analysis, in particular automatic generation of loop invariants. For last few years, 2 years only actually, not much, I've been thinking about how to use this stuff for doing quantifier elimination in the theory of the enclosed field. And I'll say a little bit about that near the end. I don't have much to say there yet. Okay, back to this. Okay, so here's so let me ground everything. So here, let's say we have these three very simple quadratic polynomials. One is a linear one. And we have x and y are the variables in the traditional sense. We typically call indeterminates in the computer algebra jargon. And a, b, c are the parameters. And our goal is to solve these equations for different values of a, b, c. So example, so you could have, say, a, b, c could be, a could be 1, b could be 2, and c could be 3, and so you get, first equation becomes x squared plus 2y squared, second one becomes 3x squared plus y squared, third one becomes x minus 3y, and you can find solutions, and then you can this thing. And you want to basically trying to find all possible solutions for all possible parameterizations. So what is the Groebner basis? So that's the motivation for introducing parametric Groebner basis. So let's start with what is the Groebner basis. And how many of you know that, so that I can skip most of the stuff? So not everybody knows, so that's okay. So I'll go very, very quickly, but I'll try to give you the intuition. It's not that easy to give the intuition of this stuff. So given a polynomial ideal generated by a finite basis, let's say 3 polynomials, it doesn't matter. It's a Groebner basis is a special kind of basis which has some very nice properties. First of all, you can view these polynomials as simplification rules. It's a little bit weird that one would never think that you can use this way to simplify things. So you take a leading term, think about James Stark, he was all the time emphasizing leading term, leading term. So you have to take a leading term and you replace the leading term by rest of the polynomial with a negative sign of it. And you can show that if you define leading terms properly, this process of simplification will always terminate. So this is the connection I had with term rewriting, and I got interested in 1982 about this stuff. So now what are the properties of this particular special basis? In contrast to what goes on in the definition of an ideal, every polynomial in the ideal simplifies to 0 using the Groebner basis, just by doing the simplification rewriting. And that's the very nice property. And obviously, mathematicians before that were using these things, but they had to do a lot of struggle to get checked for ideal membership. And that was Buchberger's major contribution. And more importantly, every polynomial has a unique normal form, canonical form. And again, use all these things using the term ordering. So the unique normal form for every polynomial in the ideal is 0. And others basically are the quotient structure that you define by the ideal, and things which are equivalent have the same normal form using modulo the ideal. So what are the properties of the Groebner basis? Once the term ordering is fixed, and I'll tell you a little bit about the term ordering, but I will not say. So another good thing is the reduced Groebner basis, where you reduce everything in the basis, Groebner basis, is unique. So this is the other sort of motivation for algebraists to study Groebner basis, because I give you 2 ideals and you want to check whether they're equal or not. And you can basically construct their Groebner basis using the same ordering and see whether they are integral. You have a question? No, I see. So for solving systems of equations, this is what you see happening in Mathematica, Maple, and other computer algebra systems. If you use lexicographic ordering, which is not a good ordering to use for computing Groebner basis, then you have a very nice structure from which the common zeros of the polynomials can be computed. You will again see some examples of that.
So did you say it's not a good order to use? Okay.
Because computation-wise, it takes a lot more time as compared to other orderings. So that's why I think, if you recall, Davenport Stark basically was saying that you can do change of basis. So you start with some other ordering and then do a change of basis. But that works very well for 0-dimensional ideals, where you have only finitely many solutions, but does not work very well on non-0-dimensional ideals. And this is again where I got interested, again connecting with theorem proving. If a polynomial system has no solution, then its Groebner basis is a constant. That's basically I started thinking about this thing in the context of geometry theorem proving. I could set it up with a geometry problem formulation as a refutational problem, like typical what we do in refutation style theorem proving, and all I had to do was to check whether the result was essentially 1 or not. So what is an ordering? So, it has to have certain properties. Basically, we want to ensure it's well-founded. That's the whole idea. So t, any term t is greater than or equal to 1. Term by term, I mean variables raised power some exponent. And if t1 is greater than or equal to t2, then you multiply it with any other term or any other polynomial, then the ordering is preserved. That's all. Those are the only 2 conditions you need. So this now, once you have this ordering, you can take any polynomial in simplified form and pick the leading term. Essentially, you don't have to worry about the coefficient, especially if you're working on a field in the rationals or complex numbers. But if you're dealing with integers, then you have to worry about the coefficients also. And then you just use the ordering, the polynomial as a rule, so, rewrite rule and simplify it using Tugan determination. So how do you get Groebner basis? So this is the idea of notion of critical pair that we use in term rewriting or superposition that Constantine will talk about later on, but Buchberger called it S polynomials. And I'll give you an example of that also. So the whole goal is, since you have this rewriting now, which is terminating, all you need is local confluence, or which will give you confluence, and so we basically have to have the Church-Rosser property. That's all we are looking for. And that's what Buchberger's algorithm essentially ensures. And another great thing, which is not the case in general, with group Bendix or even on string rewriting and all that, the algorithm terminates. It has very high complexity in general, but it terminates. And the result at the end of termination is a Groebner basis. So I'm going to give you a very simple example and then pause and ask whether any questions you have about this stuff. Let's take these two polynomials, very simple ones. Have this picture, these intersection points, and essentially we want to find common solutions. So this is let's say we use it doesn't matter in this case what ordering you use. So I'm using lexicographic ordering. So y is bigger than x. So you get the first rule, which is y squared goes to minus x squared plus 4x, and second rule, xy is 1. And you can see I cannot simplify using any of these two rules on each other. So what is superposition, or what is critical pair? You take the two left-hand sides and you unify them if you want to take this broader view, or you basically compute the LCM, basically larger of the two exponents in each of the variables, which is xy squared. That ensures that you will be able to apply the rules on both sides. Obviously, you don't have to consider all possible LCMs and all that, so there are all kinds of criteria for determining when things are superfluous and all that. And you get this, and you can see that all this is a very nice polynomial. Y is purely in terms of x. And this is one of the nice properties of lexicographic Groebner basis when you're dealing with zero-dimensionality. You will always get a polynomial in the least variable, then next highest, and so on. There will be a lot more there. So you get this, and then you get that one, the least one. So then you solve for x there, substitute the values for x there, and all you get all the. And that is the Groebner basis, and you get all the common solutions. So as I said, process terminates.
You said you were going to pause.
No, I'm going to pause now at this point. Okay. And so, what is the basis? Okay, sorry.
So you're saying this is the Groebner basis?
That's right.
But why did you get x, y squared? Why that starting point?
Oh, in the top? Oh, so basically, look at y square and xy, there's an overlap. If I use xy square,
So
I may non-trivially be able to reduce this particular monomial. Obviously, adding them is not going to get you anywhere, because it's going to get the same thing.
So you multiply them.
You take the LCM of the two. Obviously, you don't have to take LCM if GCD is 1, so that's the trivial case. So you only take a non-trivial LCM.
So you've created a critical pair.
Exactly. This is the critical pair.
And then you order that critical pair,
Sorry?
and then you order.
Then you simplify. You go the sides, you get that, and now you
take these
now
two
you
terms
make them
and you
equal.
them a rule.
You make them equal, and you get the polynomial.
So you add a new rule making them.
That's right. That basically what you're trying to remove the divergence that is there. Since you don't have local confluence, you want to make sure that everything now converges. to the same normal form for this particular equivalence classes, and this is the process you keep on doing.
So this is like new Bendix.
Exactly.
And
So-
once I read that this generalizes Euclid's.
Right,
GCD
right,
algorithm.
right.
In which
But
sense
that's
is-
a little bit of, I think, just too,
It's
that's,
a far-fetched.
I don't know, like, I think,
Is it possible?
I personally think it doesn't, but.
Oh, you think it doesn't?
Well, it is definitely true for the univariate case.
All right.
But we are talking about Groebner basis interesting only for the multivariate case and non-zero dimensional things, and in that case,
So
I am skeptical.
in the second bullet, you say simplify the second polynomial.
Yes.
What is the second polynomial?
X, Y goes to 1. Right?
So you have.
So there's a Y there, now I have Y in terms of the polynomial and only in X.
So once you have a new rule.
Why
you
did
have
you
to
simplify
revise-
the first one?
Oh, well, that will disappear, okay, that's why. I simplify everything, but that will disappear, that's why I didn't show you.
Okay.
Yeah. So, and this is a very, in some sense, expensive process.
So in some cases, you have
Things
two,
will get deleted.
you have two polynomials that remain, and in some cases one of them gets deleted, and in this case only one of them remains.
No,
It
two
can be
remain.
more.
Two remain. Y in terms of X, and then purely X.
Yeah, but the y squared in terms
That's
of
gone, because Y plus X cubed minus 4X squared
Hmm.
is going to simplify that, and that's where the GCD computation over the univariate case will go on, eventually giving, in this case, it doesn't give you anything interesting.
Okay.
Good.
This is why we needed a pause.
No, that's okay. Anything else? Any other questions? Obviously, this is a very trivial example.
Yeah.
Things get very complicated, so don't misunderstand. But at the same time, good thing here is that they work, and often you can get results, which is not the case with CAD, cylindrical algebraic decomposition over the reals.
Just because CAD is way more expensive.
No, the same complexity.
Ah.
This is the
But
beauty
the
of this.
complexity you're talking about is in the worst case.
So
Right.
what's the termination?
I'm coming to this. So basically, this is doubly exponential in general, but singly exponential for zero-dimensional ideals, and CAD is also doubly exponential. But the problem is CAD almost never gives any output to
Well,
me.
this
at
gives
least.
only things solutions in complex space.
That's right.
So
That's,
power.
no, that's the other, yeah. So in that sense, this is more complex. This is more, it had complexity than CAD, because as he pointed out, we are solving over the complex domain, not over the real domain.
Yeah, but it's like the difference between Diophantine equations and real equation, complex equations.
I don't
Problem
think
is
so.
simpler when you get in the complex plane.
Things get simpler in, I don't know, whatever intuitive sense, but not in the, from a complexity theoretic standpoint, right? So a lot of the stuff is unknown, so. Okay, so this is the beautiful Dixon's lemma, which is used to show termination. And the idea is very simple. So basically, what you're looking at is the left-hand side, and if you look at all the left-hand side you see here, and you do comparison based on whether one side reduces the other, one particular left-hand side reduces the other left-hand side and all that. And if you look at all those tuples on the left-hand side, under that particular ordering, that's always a finite set. It can be huge, but it's always a finite set. Great. So, are we okay now? Or should I proceed on the parametric case? Things are going to get more complicated, but I'll try my best to make it simple. Okay, so back to the example that we started with. So you can see now, let's say we do specializations. Let's say specialize trivial 0, 1, 0. A is 0, B is 1, C is 0. So everything sort of goes away, and the only thing you're left is the ideal generated by single generator, y squared. And this y squared, obviously you can see easily that this particular ideal is one-dimensional, because x could be anything. Then you look at now the other one, 1, 2, 1. Then you get a zero-dimensional ideal. Because x is equal to y and y square. So y is 0 and x is also 0. So actually it's a single point. So we see that for different specializations, things are changing. And also, you will see later on, or even in this case, you can see that once you make a to be 0, y square becomes a leading term, and b is non-zero, say. While if I make a to be 1, and if x is bigger than y, then x square is going to become a leading term. So things change drastically. Structure of the polynomial changes drastically. So what is the comprehensive Groebner basis? So I'm going to make, basically, this is not the way the theory has developed, but I'm going to try to draw a parallel with Groebner basis and the parametric comprehensive Groebner basis as much as possible. That's going to be my whole message here. Okay. So what is the comprehensive Groebner basis? It is also a subset of the ideal F, such that for every specialization of parameters, specialized version of that comprehensive Groebner basis is a Groebner basis. Now think about it. We have infinitely many specializations, but this is a finite object. So that was essentially what Weispfenning and I independently showed around the same time. That this is a finite object, and in principle this object can be computed.
Does it always exist?
Huh? Always exists.
But in your case,
You'll
have
see.
2 or 3. You
Oh
have
yeah,
different number of elements,
you'll
so
see it's always going to exist, and you'll see.
yeah, different Groebner basis.
Yeah. So you'll see. You'll see in a minute.
Yes, but
So this is that.
does
This
it
is
change
the
the number of
most
elements
of the
in
talk
basis?
you are going to see.
Some of the elements disappear
No. And the other thing is, which is what George is alluding to, that what we want is that's basis that we get is very much like the old, in the standard case, it's a subset of the ideal. It's not specialized polynomials, which are not in the ideal. Okay, so this is the idea. You try to identify groups of specializations that share the same Groebner basis. Okay? And for each such specialization, compute the respective Groebner basis. So the question is, are there finitely many such groups or segments, which you're going to see later on? And the answer is yes, and we're going to show you that. So now this is the history a little bit. So this is Weispfenning 92, my paper published in 95, and all that. So all this stuff, and subsequently, see, there was a problem because it was not easy to compute this comprehensive Groebner basis, but there was very nice insight by Suzuki and Saito in 2006. After that, again, many of us started working on this stuff and thought very, very interesting stuff. Then algorithm, I'm going to explain to you what comprehensive Groebner system is, then I'm going to explain to you what comprehensive Groebner basis is, and then there's some related stuff and then attempts to do the problem that I'm going to talk about at the end. So what is a comprehensive Groebner system? So the comprehensive Groebner system is the thing that is going to do the partitioning of the parameter space. So it's a collection, it's a finite collection of pairs. The first component is constraints on the parameters, equalities and disequations, not equal to. Okay? So it's going to define a quasi-variety on the specializations. Okay? And the second component is a Groebner basis. So basically what the thing is saying is that this pointer is
That's a laser thing,
Oh,
the
good.
top.
Oh, I see that. Turn it on. Okay, great. Thank you.
On the top.
Hmm?
This one.
I have pressed that also. I see. Okay, so this one is purely in terms of parameters, and this one is the Groebner basis associated with the parameters. So all this thing is telling that. So the example, basically, these are the Groebner basis, and these are the segments. So basically what the thing is saying, for every complex value other than the one which makes ABC minus A square is equal to 0, things are okay.
So it's a disequality constraint.
That's a disequality, right? So saying C cube minus the variety defined by that. Okay, so and that's the Groebner basis there. Similarly, you can see all these Groebner bases there. But some of these things are not going to be part of the original idea, which is not a good thing. Well, although in the literature people have talked about all this stuff and all that, but it's not a good thing for me because it's not elegant. You have a departure from the Groebner basis, standard Groebner basis theory. Okay. So what is the comprehensive Groebner basis? You can, if you don't have this requirement that every polynomial is in the comprehensive Groebner basis is from the polynomial ideal, then it's just the collection of all this. But if you have that requirement, you can get rid of many of these things and you have a different set of polynomials. So the nice thing here is it satisfies my original definition. So if I take this particular Groebner basis or comprehensive Groebner basis, I pick any specialization. All I need to do is specialize this and I get a Groebner base. So this is what I was.
So it has more elements than any Groebner basis. And sometimes some of these elements cancel out.
Become redundant, right? Yes, sir.
What is the relation to a Groebner basis of the bigger system where you have the three parameters as variables?
Sorry? Yeah, okay. We'll show you
really
more also. We'll get to that actually. Totally very misleading. See, this was but that was the connection that Suzuki and Sato made, which was not at all clear. But from there, you have to do some lot of more stuff. That's where the problem is. Okay. We'll see hopefully more in this. I'm glad that there are these questions being asked. Any questions on this example? Okay, let's start now. So this is what you alluded to. So let's first, so how does a typical algorithm after Suzuki and Sato works? Before that, Weispfenning's algorithm as well as my algorithm was very, very complicated. It essentially was basically looking at the polynomial, parametric polynomial, doing case analysis. Leading coefficient 0, leading coefficient not 0. So building these trees and trying to compute. Obviously, it's easy to see that that tree is also going to be finite. And that's how we basically did. As I did certain optimization because of which I got some slightly better results. That was essentially it.
Question. So was it feasible paths through that tree that ended up giving you the constraints on
Yes.
the
Yes, all the time. Basically, the tree is a node. You can think about a node in the tree being up to this point. These parametric constraints are equal to 0. Other parametric constraints are not equal to 0. Because basically you're saying, let's say from the previous example, A is equal to 0, A not equal to 0, then A is equal to 0, B is equal to 0, B not equal to 0. So that's the way you build the thing. Now, I don't know, you said, or you said that, Tarski's original procedure also does something similar, which is possible. I thought I had read the paper, but that was ages ago. So you can see very high non-elementary complexity of Tarski's procedure is probably because of that. But luckily here, in our case, it was still doubly exponential, sadly, or bad. Good thing because there is no way you can avoid that. Okay, so this is the other good thing. So when you try to take a parametric system for certain parameters, the Groebner base may be 1. So there's no solution. And that's where I see a lot of usefulness of this idea in the context of quantifier elimination or real closed field. Because if there are no solutions over complex number, there are no solutions over the reals either. So this is so what is going to happen is we're going to compute the Groebner basis using this block ordering, and I'll explain to you in a minute, where variables are bigger than the parameters. So, and that essentially assumes that most of the parametric constraints are not equal to 0. And then we are going to consider one by one the parametric. This is where we go back to the original construction and start doing that, building the tree that way. It turns out that tree is much smaller and a lot more compact than the trees both Weispfenning and I were constructing. And that's the new insight. Okay, so I'm going to show you examples. Okay, so this is where, so there are two key ideas among a set of polynomials which are candidates for inclusion in a Groebner basis at any particular branch. All we need to consider are the least polynomial in the leading term. There could be many polynomials with the same leading term because we have parameters which are different, could be ax squared, bx squared, and all that. So you consider only after the specialization the least polynomial in the leading term. Hopefully you'll see examples of this thing. Okay, so that's the thing. So using what you were saying, you can compute the Groebner basis just without worrying about whether some variables are parameters or not. But you have to use the ordering that the indeterminates or the variables are bigger than or equal to parameters, because they're going to be the least one. So this is the Groebner basis you get. So now you do this kind of thing. So obviously, okay, let me give you first idea. Okay, so let's look at this thing. Let's say the ordering is, what is the ordering? X is bigger than y, right? So we have a term in X. We have a term xy. So all we need to consider is this particular term for the Groebner basis where a is not equal to 0. Then similarly, y, we have a y square, y square, y square, y square, y cube, y cube. So all we need to consider is one of these two, 3, and whichever is the least in terms of parameters. So that's what the other new insight that we had based on Suzuki-Sato's idea, and that gives you much simpler stuff. So the first one is this. Okay, and obviously, what is the condition? Condition is a is not equal to 0, bc minus a is not equal to 0. Because you want to make sure the leading coefficient is not 0. So what do you do next? So that's okay. So this is the first branch. Well, it's possible that you may also, when you compute this Groebner basis, you may get polynomials purely in parameters. And that's why it's important to use this block ordering. That corresponds to the case, where for those parameter specializations, there's no solution.
So your order is lexicographic.
It doesn't matter actually. But you know, the only thing is that x, y has to be together, has to be lexicographically bigger than ABC. So that's what is meant by block ordering. But within ABC, the ordering could be anything. Within XY, ordering could be anything. But every term that involves X has to be bigger than everything that involves ABC. And similarly for Y. So that's what the notion of block ordering is, intuitively speaking. Yes. So that's this. So if we had gotten, I think I have examples later. If you had gotten only things in terms of parameters, so those are the basically cases where there's no solution. So in that sense, very nice from the point of view elimination and all that. And then otherwise you keep on doing things. So now we got this branch. So what are we going to do? Obvious, a is equal to 0. And then do what happens, simplify the thing with a is equal to 0 and compute another Groebner basis. Then BC minus a is not equal to 0. And keep on doing this thing.
So you choose a is equal to 0 because x is ordered before y.
Well, yeah, but it doesn't. Okay, so there's an interesting this mode of heuristics now. Which one to choose?
No, a is parameter. Right?
Yeah, a is a parameter. That's why, not x because of x. Sorry, yeah, that's a good point. These
No,
are.
I understand, but between the parameters,
yeah.
you choose a condition on A or a condition on C.
BC minus a, you mean? BC minus a, right? Whole thing together, not C. Now you treat these things as okay. Sorry, maybe I should have mentioned that too. Once you compute this, now you treat as these things are parametric polynomials,
But the
purely
question,
in the variables.
the question was, when you pick Ix minus Cy, why
Uh-huh.
don't you specialize
Oh,
C to
oh,
0,
oh,
but
oh,
I to
oh.
0?
Yeah.
Yeah,
Yes,
because of
I
x greater than y, right. Right. So you always look at the leading term
Okay, so you chose that
Right,
an
sorry.
order that makes the leading term to
That's
be
right.
x.
to be 0. Because our goal is always to consider the case where leading term is not 0 or 0. And keep on getting new leading terms that way. Sorry, yeah, thank you very much. So this is the first branch, a not equal to 0 and bc minus a not equal to 0. So now we start with A is equal to 0. So all you need to do now is whatever Groebner basis we have computed, you add A is equal to 0 there. And hopefully things will become a lot simpler, which happened in this case. So now you have this. We have already taken care of A is equal to 0. Now we have Cy to be the thing. So C is not going to be equal to 0. So that's another branch. And then you also have a Cx squared. So you get this. That's the second branch. And that branch corresponds to the case A is equal to 0 and C is not equal to 0.
Why did you keep the C with the Y?
Huh?
Why did you keep the C with the Y?
Well, because x is bigger than y. Right? So we have cy dy squared cx squared. So we pick the least term again in y and then x.
Yes, but if C is non-zero, Cy and Y.
Oh, no. So you're now thinking about solutions. I'm not thinking about solutions yet. So basically what we are trying to do is we have C A is equal to 0, we know that, but Cy could be non-zero. So C is, in that case, C has to be non-zero. So that's why you're picking C. Now that will make Y to be 0 as a solution. Yeah, but that is a later step. Once here the goal is to compute the Groebner basis, not yet looking at the solutions.
Yeah, okay, but Y would be a equivalent basis.
Why? Oh, I see now. Cy, when C is not equal to 0, you can divide by C, you're saying. Yeah, that's, but then you're going to get problematic, you're going to get rational functions in general. Because C may not be a factor everywhere. But if C is a factor, yes, you can do all that optimization.
Could be Ci plus 1.
Right, so here, for example, Cx squared plus y squared. If you divide by C, you're going to get 1 here and 1 over C here. And that gives you rational functions, and that's another ball game. So that gives you the second one where A is equal to 0 and C is not equal to 0. And you can keep generating branches, and that's how you get all these branches. Okay, any questions?
Do you need to go recursively after that?
Recursively in the sense you could do the reduced Groebner basis.
Yeah.
Right. Yeah, that is very good there all the time.
So by the way, when you assume something's non-zero,
Huh.
you could also imagine having another indeterminate where you add in the, for instance, let's say we assume Cy is non-zero, we could then say have a Z and express that by saying Cy minus Z equals 1.
Yeah, it's tough.
Okay.
And more things you add, more trouble there's going to be, right? Because the complexity is dependent on number of variables. Right. But there, the nice thing is you're trying to make as many parametric constraints equal to 0 as possible. Right. So this is you get the comprehensive Groebner system, but as I pointed out earlier, the Cy is not in the original idea. So so how do we get rid of that Cy and get something different, which is whose instantiation is in the ideal? So I said that. So this is the idea of faithfulness, which is also what we introduced later in 2010, 2011. Namely, we want the polynomials in the comprehensive Groebner system as well as Groebner basis to be part of the original idea. They should not be this. So we came up with a representation which is basically trying to do bookkeeping and all that, and we succeeded. Okay, so split the polynomials in 2 parts, 0 part and the non-zero part. Actually, both Weispfenning and I had this idea in our first paper. Actually, I definitely had the idea. It's a hidden Weispfenning. So he used colors to define these things and all that. So mine is a lot more explicit. Okay, I'm going to skip that. Okay, so here are the sort of key features of the algorithm that we came up with in 2011. It partitions the parameter space into the disjoint fewer branches. Very, very few, very in the sense of examples, not in the sense of complexity and all that. Segments. Output is always faithful. All polynomials CGS and CGB are in the input ideal, and it's sufficient. Not only we claim it, but the other people who used our software claim it.
So the
So efficient
efficiency.
in an empirical sense.
Huh? Oh, all empirical, yeah. So all otherwise, all worst case doubly exponential. Yes, sir. With a
I
question?
had the same question.
I see, okay, yeah. So everything is empirical here. Okay, but things work. Like in the sense you can get results, and I'll show you some tables and all that. And another nice thing is CGS is minimal. Groebner system is minimal, and I'll explain to you why that is. It's reduced also. For any branch, any specialized in this branch, the corresponding Groebner basis is the reduced Groebner basis and minimal. For every branch, the set of leading terms, you get a question.
But it's minimal, this means that it's not unique.
Huh?
It's not unique.
It's unique for that particular specialization. But some of the things may not be, see, you have to simplify them. That's right. Right. But because, see, the leading terms are always going to be non-zero. That's the crucial thing, right? Because there is only one leading term for polynomial. And that is non-zero because the way you construct it. So that's the reason.
But you can't in general get it reduced.
You cannot in general get it reduced.
And sorry, one more question about the output being faithful. So I see why that's a beautiful, desirable theoretical property. But in practice, let's say you just care about having this comprehensive Groebner basis to do individual specializations, sort of on demand. Do you really need it to be faithful?
Probably not. So I'll tell you also later on why this thing I'm getting there. But that's again a theoretical, thing. So I'll get to that in a minute. And the other great thing is the G Groebner basis is stable, related to what you were saying. That it doesn't change for different specializations. For that particular segment of specializations, it's remain the same. So they can see that we could do these things. A lot of hard in the sense, like hundreds of examples. Pretty.
These are seconds.
No, seconds, yeah.
So the examples, they are taken from a well-known place.
Yeah, reasonably well known, right. But more interesting examples are in geometry, and they are still tough. More than an hour. But this one, new version, could do it in 14 seconds.
So is reduce in that case actually trying to compute a comprehensive Groebner basis?
Right, they have an implementation, I think it's original Weispfenning students like Thomas Stern or somebody else's implementation. Right.
So your algorithm is implemented on top of the singular
That's right.
system.
There are two systems implemented on Magma and Singular. Because those are somewhat specialized for Groebner basis computations. But basically, it uses the internal data structure of those things. We did not play with any new data structure, and they don't have any comprehensive parametric polynomial computation. So basically, you have to rely on that. So in principle, if you could start from scratch, you could do better. And this idea that we talked about, it could be used in any system. So now let's say, what is it? Okay, so this is just saying the same thing. Okay, so to get, what I'm getting to now, we can at the end make CGB to be monic. Monic in the sense, because my goal is to get towards minimal comprehensive Groebner basis and eventually canonical comprehensive Groebner basis. Very similar to what goes on with Groebner basis theory. Okay, so monic essentially means that the coefficient of the leading term in the comprehensive Groebner basis is going to be a polynomial in the parameters, so you make that polynomial monic. So that way you can compare them differently. Okay, so this is, let's say, this is another example, very simple example again. So these are the branches. Okay, 4 branches, and you can see like V is equal to 0 and U is not equal to 0. It's no solution. V is equal to 0, U is equal to 0. The ideal is 0 ideal. So because it's not very interesting. But you have otherwise y square, x square, and all that. Okay, so this is the CGB, 3 elements. And these are the branches. So here is what we have so far. Minimal, proper subset, not GB. Okay. Here also in the comprehensive Groebner basis, proper subset, not CGB. Leading coefficient 1, here leading coefficient is monic. Reduced, polynomial normal form. no result there yet. Okay, canonical, GP, reduced GP is canonical with respect to every ideal. Once you fix the ordering, no result there. Okay, now how do we get minimality for CGB? So we would like again the same definition there as essentially that no proper subset of CGB is a CGB ideal. Uniqueness, it should be uniquely determined, same thing. And what do various, here I'm going to just list them all. All the algorithms before our paper which appeared in 2015, ISAC, all the polynomial, basically algorithms are neither minimal nor unique. Basically, everything, including our own. Okay, so how do we get a complete minimal comprehensive Groebner basis? But maybe before that, any idea? Things are going to get a little bit more complicated, so if there are any questions, I'm happy to answer. 10 minutes, right? Hopefully I will finish in 10 minutes.
I don't understand. Are you supposing that you are working on the field or on the ring? Is it works also on the ring?
The specializations are over a field,
Okay.
right? But the parameters thing is a ring. Since I had too many symbols in almost every slide, I got rid of a lot of symbols. So, you have K, U, and X is the ring that I'm computing the reduced Groebner basis on all the time with constraints on the parameters. But things I'm interested in are parameters specializing over a field or a quasi-variety. So since the same one, coefficients will be from a field.
Coefficient will be from a field and the ring of parameters.
No, the ring of parameters will get specialized to a field, right? That's what is happening.
So this means that the A, B, and C are taken from a field.
That's right. No, that's another interesting issue, like what do you do when they are integers? That's another, anyway, not get into that. Okay. So that's what we have so far, and I'm going to attempt to fill at least the third row, and fourth row I'm going to give some ideas. Okay, so this is good. Okay, so what do we do? First, basically one way of thinking about this whole thing is you compute the CGB, say, using our algorithm. Okay, then there's this notion of redundancy, or non-essentiality, whether the polynomial is essential or not. And that's different from reduction, and you will see examples of that in a minute. Okay, simply, essentially in the context of standard Groebner basis theory, reduction or simplification gives you minimality, and this thing simplifies things and all that. But that is not possible here. And we'll see a very simple example. So simplify essential polynomials while maintaining the CGB-ness. So you want to do two things. You want to identify non-essential polynomials, get rid of them, and you want to simplify essential polynomials so that they are lower in the ordering than these things if you want to get a minimal basis. So that's it. Okay. So let's see what is it written now. This is going to get a little bit difficult, but maybe I'll go an example first. Okay. So this is the original, very simple ideal. Generator, two generators, uyx plus yz plus x plus 1. Okay, so this is where our partly your question will be answered. So you compute that, say, with the reduced Groebner basis and all that, and then other things. You will get only FG. FG is a reduced Groebner basis. Okay, but in a comprehensive Groebner basis, you need H also. What is H? H is the difference of two polynomials, G minus F. And why is that? It's a beautiful example, I think, due to Weispfenning. So like if U is equal to not equal to 0, we have this particular polynomial. And if V is not equal to 0, we have essentially U is not equal to 0, V is not equal to 0 is covered by these two polynomials. If I make U to be 0 and V not equal to 0, that's also covered by these two polynomials. Similarly, the other case, but when a u and v are 0, then you have x there and x plus 1 there, which is unsatisfiable, they have no solution. And that's what this thing is compensating, h, g minus f. So reduced Grosvenor base is going to give you 2, and that's not even a CGP.
But why do you also need minus h?
Huh?
Why do you
Oh,
also need minus h?
so this Weispfenning originally it reported these 4. I don't know why. Okay, so we basically essentially then figured out. So one of this thing is essential, not essential. So how do we compute that? So as I said, essentiality check is non-trivial. So what do we have? Let me give you the intuition first, and then we can go back to the technicality. But maybe I don't have time to do technical. Okay, so what we want is all the polynomials. We have to check whether they are really needed for some specialization. That's the intuition. Because if they're not needed for any specialization, then you get rid of. You don't need it. So if you look at this, we know this thing is needed for specialization because v is equal to 0 and u is equal to 0. Here the leading term in other things is x, both cases, while here it is 1. So that's the check essentially what is going on. There are various segments you try to check what is needed, what is not needed. And that's why it gets expensive.
So how many segments do you have for
Exponential.
Well, yes, in general, but for these examples.
This example is only 2-3 segments.
No, but you had a list of 10 examples.
Oh, those examples, like I think the worst case we had about 50 or 70 segments, something like that. Less than 100 segments. But you can have many, many segments. Okay, so basically what we want to do is we want to compute a non-empty subset B of the parameter space such as a particular polynomial has no covering. And then it's essentially, otherwise not essential. And that's basically the idea. And since I'm running out of time, I'm going to go to the main thing later on, which is an open problem, at least so far for us. So there's another example, and you can see we have 4 polynomials here, and only 3 of them are needed. Which 3? That's another again mystery here. They're all minimal. Where is it? Okay, this is showing the details, but I will not get into the details now. Okay, so this is a minimal. So this way now we can get minimality and all that. But these are all the minimal polynomial sets. So they are not even unique. So that's another complication. Okay. But you can compare them because you have a well ordering or a total ordering on polynomials, which you can extend to total ordering on finite sets of polynomials. So you can compare them and you can get the least one. So then you will think that this least one might be the canonical one. The answer is no. Well, that's what okay. So that's the punchline now. So recently I proved, this paper is appeared in January, that obviously this was known, like at least we had at least talked about that before. You know that a canonical object exists because as I said, because of the well ordering principle, essentially, if you use that Zone's lemma and all that, you can get that. That's not very satisfactory if our goal is to get a algorithm. So then I proved this, and I basically show that there is something without resorting to well ordering. Okay, for each, okay, so let's look at this. This is now the original construction that is there in the Groebner basis. There are many characterizations of Groebner basis. There is a characterization in terms of leading terms. If you look at the leading terms of all the polynomials in the ideal and order them by this ordering, that one doesn't reduce the other one, that's a finite set. That's one characterization of leading terms. So if we take all possible specializations of the ideal, look at all the minimal leading terms for each of those specialized ideals and take the union of the whole thing together. Okay, that's this. The question is this finite or infinite? So I prove in the paper that it's finite and it's also a comprehensive Groebner basis. Okay, so this is basically parallel to the construction that is there in the standard GCB, analogous to that. But this particular CGB may not be minimal. So you have to get rid of the essential terms from there, or non-essential terms from the redundant polynomials from there. Now, once you get rid of that, the result that you get is the unique canonical CGB. But how do we compute it? So far, I've struggled for 4 years, no idea. Okay, so there's a theorem in the paper I wrote that there exists, and this way construction works. So we thought, okay, it's this way of computing CGS and CGB, although very nice and useful for many applications, is not getting anywhere. So let's try to come up with a completion-like procedure for computing CGB directly. So maybe that will give us a canonical CGB. So we wrote a paper which appeared in last year's Isaac on a completion procedure, basically very much like original Rupert-Gers or Knuth-Bendix completion procedure, which does not go through CGS and all these constructions and all that, but goes directly to compute the group. But it doesn't produce a canonical CGB. It produces a minimal CGB, but not canonical. So a future work, algorithmic construction of this thing, like approach. Okay, so this is the thing that I thought I'll mention the last few minutes. So how do we go about basically using this stuff for speeding up quantifier elimination over the reals? Obviously, one thing we can do first is to take the equalities that are there in the system, get rid of all the even non-strict inequalities by making them the disjunction and all that, and then use this simple heuristic which works many cases, that if you have some polynomial which is sum of squares and that is greater than 0 or equal to 0, sorry, then each of those polynomials have to be equal to 0. And then you can of course use the dual universal charts and all these other things and all that. But this seems to go a long way, at least in proving geometry theorems, because they are typically you're dealing with degree 2 polynomial. I'm talking about two-dimensional Euclidean geometry, where you have ordering relations and all that, which has been another issue for a long time, ever since like Wu came up with a way to deal with it in the 80s. So the other thing is again theoretical in nature. Okay, then I just mentioned the issue that James was talking about. Computing a certificate in the case of Groebner basis is a problem. Here it's going to be even more complicated. And think about it in the context of CAD. I cannot even imagine how the certificate will be produced in CAD. So that's why I said, so analyze polynomial equalities and generate segments on free variables. Use that as the starting point for every, sentences are not properly stated there. Okay, and then goal is to develop a sufficiently large set of heuristics for performing quantifier eliminations of polynomial equalities and inequalities. And the two classes that I am interested in is basically geometry formulation and Euclidean geometry, where I think I have basically a pretty good, decent solution. And the other one is for loop invariant generation for programs and hybrid systems. And put it into this. That's it.
Questions?
Are there competitions in which you can compete with other algorithms?
There are no competitions that I know of. But there are implementations, and there is another very different, I did not mention this, there's a very different way of computing Groebner basis that is credited mostly to Audrey from Perry, and he was a Lazard student. And actually Lazard had the original idea, basically convert everything into linear algebra and do linear algebra computations. And so that is considered to be one of the best ways of computing things. But that works only for a very special subclass of polynomial systems.
Can you say more about the certificate generation problem? What's the
Well,
challenge?
basically, if you recall what the downput was talking about, for example, if you want,
I
you're
was
starting,
not here.
oh, you were not here, I see. So you have an ideal basis, okay? And you want to find out, basically, I give you another polynomial. Is that in the ideal or not? Okay, so you're going to compute the Groebner basis and then use that to simplify. That's one way of doing it, okay? But Groebner basis is not the original basis. So you can actually do bookkeeping and then come up with every element of Groebner basis to be represented as a linear spiral. Linear in the sense of a polynomial summation of the original basis. And then use that to get the thing, and that's the certificate. And that's very complicated in the sense that it's going to be, it depends on how many reductions you need in each of these cases, and that's going to be a huge object. The coefficients at least.
So the alternative is, of course, to do correctness proof. Like Wang's done.
Yes. Yes. Yep.
Yeah. I'm curious. What's the efficiency comparison of the verified procedures?
I don't know. He knows that better than I don't know. I have no clue.
I think it's like Tom M's presentation.
600.
So only 1,000
Yeah,
or 100
it's-
or what is?
The problem is at some point you also have a problem of memory because Groebner bases tend to fill use memory space, and encoding in the theorem prover are often very efficient, for example, for coefficients. Will time.
So perhaps there are hybrid strategies. Some things done by certificates and others by.
I think in terms of, I don't know whether you looked at that or if there is any interest in terms of coming up with a simpler certificate. The other algorithm, Polynomials algorithm, might be better because that's purely based on linear algebraic rules. But there's a complicated issue there also because there are a lot of things that are done, well, shown to be superfluous, so they don't need to be done, but that could be proved. So that might be one reasonable step in that direction.
And I remember when we were tackling Groebner basis with geometry, we had problem with degenerated cases.
Mhm.
This completely fit the problem.
This is where I got interested in parametric stuff, right? Because basically, parametric stuff is going to tell us under what cases the original problem is unsatisfiability of the original formulation. If you do it reputationally, so those are the degeneracies.
Any other questions? Okay, let's thank Deepak again. 1:30 constant. We'll talk about superposition.
Related things, but close to the theorem.
What's positions? Both parts.
Superposition.
Yeah.
No,
Supposition,
include bendings as well. Three.
He's going to show how to generalize the notion of S polynomials.